Hello students, I'm Miss Slate and welcome back to Chemistry A. Today we're going to talk about how to write the names for ionic compounds. First, let's start by talking about binary ionic compounds. Binary meaning ionic compounds that are composed of just two different elements. So, with the way ionic compounds are written, and this is true for the name and the formula, the cation, the positive ion, always comes first, and the anion or the negative ion always comes second. So cation first, anion second. When we're writing the name, the cation is going to keep its same element name, and the anion, we're going to change the ending of the element's name to IDE. So for example, NaCl, sodium keeps its name because it's the cation. Cl is chlorine, but we're going to change the ending of that name to IDE and make it chloride. Likewise, with our second example, Ca is calcium. The cation keeps its element name. And the anion is bromine, which we're going to change the ending to IDE and make it bromide. Pause the video for a second and see if you can write the names for the next two binary ionic compounds on your own. All right, Al2O3. Al is aluminum. It keeps its name. O is oxygen. We're going to change the ending to IDE and make it oxide. CS2S. CS is cesium. It keeps its name. S is sulfur. We're going to change the ending to IDE and make it sulfide. So it's relatively easy to write the names for binary ionic compounds. Now, if in our binary ionic compound the metal is a transition metal, we need to add something to its name because transition metals can form multiple ions. Okay, so something like nickel can be a +1 or a +2. So as a reminder, remember the transition metals are all of these elements. Some of our other metals like tin and lead will also need can also form multiple ions, so we need to add something to their names. There's two ways to go about this. There's the stock system, which we see most commonly, where we use Roman numerals to represent the charge of the cation. So if it were nickel +1, we would make it nickel Roman numeral 1. The other way to do it is with the traditional naming system, where we take the Latin name for the element and we give the higher charged cation the ending to its name of IC, ic, and the lower charged cation, we give the ending to its name OUS, aus. So the stock system is the most common way that we do it, so that's the one that we're going to start with. So Cu2O, I know that it's going to be copper. I'm going to need some Roman numerals to represent copper's charge. And then O is going to be oxide. So to figure out what the charge on copper is, we have to use the ratio of the ions and the charge of the anion. So according to our formula, we have 2 copper ions present, and we have 1 oxide ion. So then we'd go to our periodic table. Oxygen is right here in group 16, which means it has 6 valence electrons. If it's got 6 valence electrons, it's going to gain 2 electrons to get to 8, and therefore form a -2 ion. Well, one thing that always has to be true for ionic compounds is that the total charges of all the ions have to add up to 0. So the only way for 2 copper ions to combine with a -2 oxide and have the charges add up to 0 is if each copper is a +1. So for the stock system, I'd make it copper Roman numeral 1. Same kind of process for CuO. Again, Cu is copper. It's going to need some Roman numerals to indicate its charge. O is oxide. But this time, the formula says I have one copper ion combining with one oxide. Well, we said oxide forms a -2 ion. In this case, if it's a 1-to-1 ratio, the only way for those charges to add up to 0 is if copper is a +2. So copper, Roman numeral 2. Now, like I said, the traditional naming system takes the Latin name for the element and makes the ending IC or OUS. So Cu2O, that's copper +1, that's the lower cation charge. So we take the Latin for copper, cuprum, and we make it cuprous. Oxide. CuO has the copper +2, the higher charged cation. So we make this one cupric oxide. Now you don't have to worry about memorizing the traditional names, because if you flip to the back side of your common ion chart, it gives you all of the traditional names for many transition metals. So you can always refer to your common ion chart for the traditional names of ions. Now let's pause the video for a minute and see if you can figure out the stock system and traditional names for the 2 iron compounds. All right, let's check these out. Again, Fe means 1 iron ion, O, 1 oxide. We said oxide's a -2. So in this case, iron must be a +2. So we're looking at iron, Roman numeral 2, oxide. For our second one, this one has 2 iron ions and 3 oxide ions. Well, that's a total negative charge of -6, which means we have to have a total positive charge of +6. Well, the only way to get that from 2 iron ions is if they're each a +3. So the second compound would be iron, Roman numeral 3, oxide. Now, the iron 2 ion is the lower charge, and the iron 3 ion is the higher charge. So FeO would also, in the traditional naming system, be ferrous oxide, while Fe2O3 in the traditional naming system would be ferric oxide. And again, the traditional names can be found on your common ion chart. Lastly, let's talk about naming ternary ionic compounds. Ternary meaning ionic compounds that have more than 2 elements. If they have more than 2 elements, they involve what's called a polyatomic ion. And a polyatomic ion is an ion composed of more than 1 atom. So when you write the names for these, the cation, the positive ion, just keeps the element's full name. For example, with this first one, Na is sodium, so we still write sodium. The negative ion, we need to use the polyatomic ion name. So polyatomic ions have special names, and they're all listed right on your common ion chart. So again, for this example, I'd find C2H3O2 on my common ion chart. When you do, you find that the name is acetate. Likewise, in this example, Al is aluminum, so it keeps its element name. I just write aluminum. And then Cn, again, if you look on your periodic, or your common ion chart rather, you will find Cn, and it is cyanide. Pause the video for a moment and see if you can write the names for the other 2 examples. All right, this example right here, Mg is magnesium. C2H3O2, again, is the polyatomic ion acetate. Now this one is a little bit tricky, this last one, because both the cation and the anion are polyatomic ions. Most polyatomic ions are negative, meaning they're anions, but there is one positive polyatomic ion, NH4 with a +1 charge, and that is called ammonium. And then NO2 on your chart is nitrite, ITE. So when we go to write the formulas for ionic compounds, there's kind of 3 steps that we need to do. The first step is that we need to determine the symbol and charge of each ion. Then we need to determine the lowest ratio of ions that will produce a neutral compound. So in other words, how many of each ion do we need to make all of our charges add up to a net charge of 0? Lastly, we're going to write the chemical formula using subscripts to represent the ratio of the ions. So first up, strontium sulfide. Strontium forms a +2 ion, sulfide forms a -2. Well, +2 and -2 add up to 0 all by themselves. So that means this is going to be a 1-to-1 ratio of strontium to sulfide. So for the formula, we just write SRS. Sodium nitride, on the other hand, sodium forms a +1 ion, nitride forms a -3. So we would need 3 of our sodium ions to balance out the charge on nitride. So this is going to be a 3-to-1 ratio. So it's that ratio that we represent in the formula. So our formula is Na3N because we needed 3 sodium ions to cancel out the charge on nitride. Next up, calcium phosphide. Calcium is a +2 ion. Phosphide is a -3. Well, remember, the lowest common multiple between 2 and 3 is 6. So to get our charges to add up to 0, we would need 3 of our +2 calcium ions and 2 of our -3 phosphide ions, a 3-to-2 ratio. So our empirical formula is Ca3P2. The next example is barium nitrate. Remember, ATE tells us we should look at the common ion chart to figure out that ion. But barium's a +2, and from your common ion chart, you should see that nitrate is NO3 with an overall -1 charge. Now, +2 and -1 don't add up to 0. We're going to need 2 nitrate ions to balance out the charge on barium. So this is going to be a 1-to-2 ratio. Now, any time that we have to show that we have more than one of a polyatomic ion, we need to put the formula for the ion in parentheses and then the number of the ion outside of the parentheses. So our formula becomes Ba parentheses NO3 with our ratio 2 on the outside so that we're showing we have 2 NO3s. Now, pause the video for a minute and see if you can figure out the ions and formulas for copper 2 sulfate. Well, fortunately, if it's copper Roman numeral 2, it's telling us that copper is a +2 ion. Sulfate is on your common ion chart, and you should see that it's SO4 with a -2 charge. Well, +2 and -2 add up to 0, so this means we're going to have a 1-to-1 ratio. So in this case, our formula is just CuSO4. No parentheses are needed here around the polyatomic ion because we only have one of them. The next thing we need to talk about are oxyanions. So oxyanions are polyatomic anions where you have an element bonded to one or more oxygen atoms. And there is a pattern to the way that we name them. So let's look at the example of the oxyanions formed by nitrogen and oxygen. There are 2 of them. There's NO2 with a -1 charge and NO3 with a -1 charge. Notice that these 2 anions are identical except for the number of oxygen atoms. NO2 has less oxygen, NO3 has more. The only thing that differs in their name is the ending. NO2 with less oxygen is nitrite, ITE. NO3 with more oxygen is nitrate, ATE. And you will see this pattern across every oxyanion. The one with less oxygen atoms will end in ITE. The one with more oxygen atoms will end in ATE. So, like I mentioned before, an oxyanion is a polyatomic ion composed of an element bonded to one or more oxygen atoms. Now, there are more than just, for many oxyanions, there's more than just 2 in the pairing, because halogens can form 4 oxyanions. So, if you have the prefix hypo added to the name of an oxyanion, like hypochlorite, that means it has 1 less oxygen atom than the ite ion. The ite suffix means 1 less oxygen atom than the ate, just like we saw with nitrite and nitrate. Likewise, the ate suffix means it has 1 more oxygen atom than the ite ion. Again, for halogens that can form 4 oxyanions, adding the prefix per means you have 1 more oxygen atom than the ate ion. So perchlorate would have 1 more oxygen atom than chlorate. And here's another example, right? So phosphorus and oxygen, they form 2 oxyanions, PO3 with a -3 charge and PO4 with a -3 charge. PO4, phosphate, is on our polyatomic ion chart, but PO3 is not. So we would have to infer that if we know PO4 is phosphate, PO3 with 1 less oxygen would have to be phosphite. And that's the kind of stuff that you're going to have to do, because not every oxyanion is listed on our ion chart. Additionally, like I said before, halogens can form 4 different oxyanions. So BRO is hypobromite, BRO2 bromite, BRO3 bromate, and BRO4 perbromate. And so that's the pattern that you see for halogens. And that is it for naming ionic compounds.